DoD makes us do quarterly reports, and they get longer and longer throughout the year. And then you do an annual report, which is just nuts. But I also have two overdue NSF reports that the program officers haven't complained yet, but I know it's just a matter of time. They're well overdue. So yeah, I'm in reporting hell right now. Oh, and I have a colleague who's going up for promotion for full professorship, and so I got to take that seriously. That's due in a couple days as well.
Just here in Boone, Hank Corbett, who you might know.
Mm-hmm.
Yeah, he actually just gave a talk. We had dinner on Friday, and he gave a talk about Argus. And
Yeah.
I saw your name on a couple of papers. I was like, all right.
Oh, yeah. I guess I am on some Argus papers. I think I may be designated as the education lead, though I don't know. I'm meeting with Nick. Nick's the promotion packet that I have to
Mhm.
take care of this week, which should be a slam dunk since he just got $24 million for Argus. Argus got
Right.
privately funded.
From some weird company that we won't
Mhm.
talk about.
Yeah, private foundation. Um, and the rumors I hear is once the first one's built, they want to build a second one in some third world country in the southern hemisphere. I mean, so move over LSST, Ruben, because this is just so much. Have I shown you all an Argus picture in any of our meetings? Let me show you because this is just amazing.
It is crazy.
It will
That's
blow
why
your mind.
that's why I got Hank up here. Like they asked for colloquium speakers, and I was like, I got the perfect one.
Yeah,
Appalachian is really good about like introductory astronomy and engineering and physics. This is the perfect thing. Yeah.
is there another picture down here that? Yeah, let's go with
Yeah.
this one. So this is just brilliant. So Nick has built. Let me spread you all out so I can see it. He's been building every scopes, which are tiny versions of this. One lives in a prompt dome, not every, but every. Tele means far, so telescope is a far seer. Every is the Greek or Latin word for wide, so this is a wide seer. Just taking me to the Argus page. 1 second. Yeah, here's one of them sitting in a prompt dome. So it's a little prototype experiment where you have 20 or 30 little cameras, like 3.5-inch telescopes, peppered the dome, but it images the full sky every few seconds. And then he started designing Argus, which is a Star Trek reference. And he scaled it up looking something like this, but in the end, there are a number of advantages to flipping it around. This is about 1,000, I think it's 900, 8-inch telescopes in a single frame. So it's collectively a 5-meter telescope. And they all, the frame just rocks it on one axis, tracks the rotation, then goes back, tracks the rotation, and goes back. And they all look through this single window here that they just have to keep clean. It's kind of like a giant eyeball where these are the cones and rods. But the only difference is the focusing element is on each cone and rod instead of up here at the window. But this will image the whole sky every few seconds, but you can stack over cadences of minutes, hours, days. And LSST, it's going to image the whole sky every 3 days. It's an 8-meter telescope, but it's going to go point to point to point to point. It takes 3 days to tile the entire southern sky. This images the whole southern sky in one snapshot. With small telescopes, but you add those up over 3 days, and you have a lot of things that are very comparable for a fraction of the cost. And you sample on timescales, just amazing, whatever timescales you want. And the data flow is ridiculous. I don't know if it's listed here, like petabytes per night or something crazy like that. I don't know exactly what it is, but yeah, so that's been funded now. This will be built somewhere I forget exactly where it's going. This one's going in the U.S. West or Southwest somewhere.
I think
Sorry, Dan, what's the difference with LSST just that you can decide your own cadence, or does it have similar resolution?
So LSST is an 8 meter, but they have to tile the sky one frame at a time.
Right. But I still don't like what is the big gain that I mean, LSST is the most expensive thing NSF has done.
Yep.
So
Yep.
why do we need to?
Well, this will sample on, LSST can only sample on timescales of 3 days. If you're looking for things that go bump in the night, and that's kind of the point of LSST, what is changing. Here you can probe any time scale you want from seconds through days. This will be, it won't go as deep as
Okay.
LSST. So this will focus on slightly brighter things because they are 8-inch telescopes fundamentally, but you can get depth by stacking over time. So just the time resolution is crazy, orders of magnitude better than LSST.
Do you know what it's gonna cost?
24 million.
Oh yeah, okay. Well that's
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 but
much cheaper.
yeah, it's much cheaper than LSST. So
So,
just yeah, go ahead.
oh, I was gonna say the location. Rumor has it, West Texas.
West Texas. Yeah, I could
Yep.
see that.
Yeah, and then a southern location. So we can get cadences over the northern and southern hemisphere of transients, like pretty much around, all the time.
Yeah, it's going to move us very close. I mean, LSST is still the center of the time domain universe, but it's going to be. This puts us right there along with them for a fraction of the cost. So super excited. Yeah, I guess if my name was on it, it's because I think I'm education lead. He offered me or talked to me about gamma ray burst training. I'm just not interested. Been there, done that. But the education stuff is my interest now. And if this whole philosophy of learning by doing, there are kind of two modes. Collect your own data and archival resources, and this falls under archival resources. But you can imagine us taking the variable star tool, which we talked about last time, and ramping it up to deal with all sorts of different types of variable objects. We have a transient tool that we use for gamma ray burst follow-up internally. We could bulk that up, and we're exploring. Actually, I'm going to show you an MWU thing at the beginning here. I figured Lab 6 is kind of a short lab, so I'll take a little bit of time to wow you with things to come. We're exploring, and we have this one tool in MWU. For doing HR diagrams, and like 8,000 clusters, new star clusters have just been announced. And this tool that we built, even though it was intended for student level, it's actually professional quality. It produces better results than what you find in many professional papers. And so we're now exploring and building this concept of a kind of a student journal / catalog where people can submit to it, and we have statistical algorithms that separates the good ones from the bad ones, and the idea is it's fully automated, so it can handle thousands of students, unlike current student journals, which can only handle whatever the person is running the journal can read. And so it can scale, automated scale, and maintain accuracy through statistical techniques instead of human oversight. And if the whole thing works out, it'd be glorious for education. And then you can imagine taking that model and ramping it up for every type of variable and transient object that you could do with an instrument like this or other instruments. And I think it's going to be a powerful thing for student engagement, in addition to all the amazing science it's going to do. But anyway.
Argus is also, like, all the information from Argus is going to be public as well. Yep.
Yep. So super exciting. Yeah, I'm going to talk with Nick in about a week or two. We're going to have lunch and brainstorm a little bit. Okay. That was unplanned, but yeah, Argus is going to be awesome. Let's see. So I figured I'd start by showing you, as OPIS is our base curriculum. It's the one that's been around for a while. It's now serving 1.5% of all intro students out there, et cetera. But we've gotten this funding from DoD to develop a follow-up curriculum. It's a little bit more advanced, the things that we do, though actually math-wise, in many respects, it's simpler and has a greater focus on arts and artistry. So it's kind of an orthogonal curriculum in many ways. And I'm not going to spend any time kind of spelling it all out. It's 50% optical, 50% radio. And we're getting interesting education results off it already. It boosts self-efficacy just like OPIS does, but it also boosts attitudes, STEM attitudes, which OPIS doesn't seem to move the needle on. It's hard to move, in the literature, it's hard to move people's attitudes about STEM. But we're getting some positive results from MWU. We get amazing results from our summer program, Arira, and MWU is kind of an attempt to take Arira and put it in a classroom. But I just want to give you a taste. I'm going to show you one activity here. Let me open up some images. You all teach HR diagrams in your STARS Galaxy cosmology courses, or if you do the whole university semester, you do STARS. And I don't think I've shown this to you yet. If I have, just stop me. I may have forgotten. But let's see. Let's go to the sample directory here. Workshop. I think it's this one. Okay, so here we have some BV and BVRI images. They're actually stacks. In MWU, they learned how to do stacks. Let's get rid of that there. Okay, there they are. Let's make sure they're all loaded in. There's a planetary nebula in the foreground. So this is an open cluster with a lot of field stars, unrelated stars. Make sure they're all in there. There's the red. And here's the green. Okay. And first, let's just quickly make a color picture. I'm going to group them. I'm going to group them there. Let's put them all on top of each other. Maybe I'll turn off the I band, color the blue one blue, the red one red, the green one green. So we have a nice color picture here. In fact, I'll go over to display settings. I'll pick any one of them, maybe the R band, and I'll just start by percentile linking to them and changing the stretch scale just to make it a little prettier. There we go. So we weren't saturating, the brightness and contrast settings saturated the stars, and here's a fancier stretch mode. Anyway, the point is not the color image, but I mean, that just a little teaser how easy it is to make color images in Afterglow. And you'll see it can get even more involved. But here's kind of the cool thing. Let's go to the R band image, and I'll go to the source list. I'm gonna, let me just check my settings here because I was playing ahead of time. Yeah, come back here in a second. I'm going to extract all the sources in the image. I think there's 1,600. This will just demonstrate the power of Afterglow. This will probably take 20 seconds. There we go. They're all marked. And so these, it cross-correlated with the APAS catalog. So it found APAS stars. Some of the brighter ones are not included in APAS, so they weren't included here. Or maybe they're saturating, in which case they get cut off from our extraction algorithm. And if I go to any other image, there are the stars again. So let's go to the photometry tool. Okay. And I'm going to go to, it's starting to photometer them. But for this particular exercise, we want not relative photometry like we did in the previous lab, but calibrated photometry. So I'm turning on calibration to APAS. Go back to the workbench. And so now we have kind of two of these update bars. Here it calculated a 0 point. It took all the extracted stars, cross-correlated with the APAS catalog, figured out the offset for this particular image. I'm going to turn show apertures off because it slows the browser down, and did a 0-point calibration. So everything's calibrated now. And for all the stars it could, it got photometric measurements. But what we're going to do is we're going to do batch across all 4 of these images. 1, 2, 3, 4. Batch photometry. This will probably take a minute, 90 seconds at most, which is in itself impressive because we have 15, 16, yeah, it looks to be about 1,600 stars times 4 images. So over 6,000 photometric measurements. It's completed. It's putting them into an Excel table, which will then download. Okay, download it. And just like we have these tools for OPIS, we're building some more sophisticated tools for MWU. And this is the prototype. We're rebuilding it in kind of a different, not all on one page, but like you scroll down and do step by step. So the order of operations is a little clearer. I'm going to load in that file I just downloaded. And it takes a second to load because as it's loading in, it's cross-correlating all the stars with the Gaia catalog, extracting their proper motions and their distances, okay? Because we have a lot of field stars. And so here we have some HR diagrams. Maybe I'll plot B minus R versus V and V minus I versus R. So a slightly bluer HR diagram and a slightly redder HR diagram. But we got a lot of field stars here. But here's our proper motion space diagram. Most of the stars, are just all over the place, but there's a cluster and it already zoomed in as close as it could to it. And so we can get rid of the field stars by zeroing in on that cluster. And now I'm going to turn on cuts in proper motion range. So basically, these are all the stars that are moving in the same direction on the sky. And you see the HR diagram's cleaned up tremendously. There's still some scatter at the bottom because those are your lower signal to noise stars. But we have a few red giants here. And so now we have a clean HR diagram. And we can do a cut and distance as well, because Gaia has distance information. If I go too low, I lose my stars. Too high, I gain them. Or I lose them again. Something around there. 1.69 kiloparsecs gives me most of my stars. That got rid of a few other stray stars that happen to have the right proper motion, but were at the wrong distance. Okay, so now we can start fitting isochrones. There's the turnoff point, somewhere around there. Metallicity is very important. Being an open cluster, it's going to be close to solar. And what you're trying to do is match up the shape. So that's pretty close there. And then dust correction. These are intrinsic HR diagrams, intrinsic color, intrinsic absolute magnitude. And so if I correct for dust, they're going to move towards the blue if I'm taking out the dust. Maybe a little bit more metallicity, a little bit younger perhaps to get those red giants on there, more dust. Bring the age up a little bit. Whoop, too much. So you see that wasn't too difficult. And so we just dated the cluster, measured its metallicity and the reddening along the line of sight. And I'll show you even more here. Let me lock the cuts, which gives me just this proper motion range. I don't even need Skynet for this. And so I think this tool could be used in every Astro classroom where they do HR diagrams. Let me extract Gaia and 2MASS. I'll just fetch that data. It helps if you can narrow it down in proper motion space so you're not fetching too much data. So the Skynet data is kind of useful here. But you could also start with APAS and do what we just did. You type in the cluster's name, It looks up its coordinates and its size, bring in APAS, localize it in proper motion space, lock the cuts. And now we've brought up Gaia and 2-mass. So Gaia blue minus Gaia red against Gaia green, maybe 2-mass J minus 2-mass K versus 2-mass H. And you could further refine the isochrones, but they're actually pretty good. But often you get better information with Gaia. In fact, actually with Gaia here, you see how there are two trends? There's a second line above there. Those are the binaries, which is pretty cool. And I'll show you one last bit here. The EB minus V reddening. Let's go back to Afterglow. Now, just go back to the display settings here. What we did was kind of a simple color combination where we linked everything using the percentile. We went to the 1% into each histogram and called that black, and 2.5% in from the top of each histogram and called that white, and max, and then combined them. And it comes out kind of good, but we can actually do it precisely. Let's link all layers using their actual pixel values. So the image comes out a little green just because the green layer has more counts and the red layer has the least counts. But now that we've done that, we can go and calibrate these not using percentiles, but photometrically. I can measure the 0 point for each image. It's doing that. Okay, now I can calibrate based on the 0 points. So the colors are genuine now as viewed from Earth, but there was some dust along the line of sight. So I can go back in here. The dust that we measured in the HR diagram was EB minus V of 0.19. And so if you wait for a second, all the stars just got a hint bluer. In some star clusters, the corrections can be pretty extreme, like the Eagle Nebula. Everything's red until you correct, and then you have natural star colors. But these are the star colors if all the dust were removed. Anyway, I just want to give you a little demo there. But I find this super, super exciting. I don't know about you all, but after you've offered OPIS a time or two, and if you have other courses, more advanced courses where this kind of thing may be appropriate, we have 13 of these activities, half optical, half radio. This is perhaps one of the coolest ones. When I do this with my students, they're working in groups. Each group does a young, an intermediate, and an old. And they're exercises where they compare, they look back in the image and try to match up. Oh, the old ones don't have blue stars, and look for the red giants, etc. And then after they've dated their images, they hand the color images off to another group. They exchange their images, and they date the clusters just by looking at the pictures. They try to, because they've calibrated their intuition, and they get really close, typically within 0.3 in log space for the time. It's a fun, powerful exercise. Anyway.
That's really nice, Dan. I have a pretty painful upper level Python notebook activity that I have our advanced students do where we query the Sloan, and this is much slicker, but we do the overplotting of isochrones, and it's a much more painful process. This might be a fun way for them to check their results.
Yep, and you're welcome to use this for the whole thing if you want. And we are building a newer version of it that won't be so compact with the weird kind of counterclockwise progression around here. It's going to be more linear. It will scroll. And once they get the results, they'll be a little bit farther down the road. We'll have this catalog they can submit. They get a publication. We'll have a DOI number on it, hopefully. And anyway, I don't want you up all the time with that. I did want to show you one more thing with Lab 5 before we race through Lab 6. So Lab 5, here's our video, but I added a supplemental video. It's a little old now. Some of the buttons have changed in Afterglow, but some more tools on analyzing your RLIRE data. You know, right now you're probably using archival data because Tololo's been down. And so these are Southern Hemisphere objects. Maybe you got some data from Meckering. If you're using the sample data, everything works as I showed. But if you're collecting your own data, you may run into a few little hiccups. And so I wanted to walk you through that. So let's load in a different data set. This one. Now, I think these were all taken from the same telescope in Chile. Let's see if I can remember where the stars are. Yeah, I got my finder chart here. That was one of them, and this was the other. Oh, I got to get into sources. Clear out everything. Okay. And turn on the apertures there. Okay. And so let's just grab all these and batch them. This doesn't take too long. Just like we did before. Actually, it's faster than this. Oh, I have the APAS turned on. That's why it's taken a long time. Turn that off. Okay, I'm gonna run a new job there. I'm just gonna run one more time, just make sure. Yeah, so it's real fast unless you're doing the APAS calibration. Download it. I downloaded it. There we go. Skynet plotting. Let's go to the variable tool. Open that up. The variable one appears to be the first one. Periodogram 556. Okay, and so this illustrates we have this one point that's really low. And it's because there's a bad pixel in the aperture. Now, if you're using stuff from the sample directory, none of these have this, but if we move to you collecting your own RLIRE data, so you may encounter things like this. And this one here, well, I don't know, but at least this one is off. And as the students are trying to find their average value, they'll say, well, that's the high, that's the low, the average is here. Where actually that's the high, that's a low, and that's just a bad measurement. In fact, we can see it here. I think it's image 42, if I recall correctly. If I play with the brightness and contrast, you'll see it there. See it? That pixel right there. If I go back, it's in, so that's messing up the measurement. So one tool that you can do is under Advanced Pixel Ops. We have this thing called kernel filter. You can select all your images and do a median 3x3, overwrite. There's no status bar on the Pixel Ops page, but it doesn't take too long. Here we go. See, the pixel's gone now. So if I come back to the photometry page, and I'm going to batch these again, download it, upload it. See, that got rid of it. So if you encounter something like that, that's something you can do, and I'm going to build it into the instructions. And I'll show you one last thing with this. If you're collecting your own data, you very likely will end up mixing and matching telescopes. All the sample data is from a single telescope, but if you mix and match telescopes, they all have different pixel scales. If you're using constant aperture photometry, I think this is currently set to a 5-pixel aperture, radius aperture. But mixing and matching telescopes with different plate scales, sometimes you may want more or less, and it becomes a case of apples and oranges. So we have an advanced photometry technique. Instead of constant aperture, you could do adaptive aperture. And I'll pop back here. And this one's pretty, you can see a little bit of, well, what it does is it scales the size to be optimal, but it also will scale the shape. I think a good one is number 7. I didn't want to add another point here. Let me get rid of that. This image is a little wind blown. And so all the stars are streaked a little bit, but adapts to it both in size and in shape. Now this would be just a tad slower to run. I mean, the other one was kind of instantaneous. This is probably 30 seconds. So we've done the median filter correction, adaptive photometry, so you can mix and match stuff from other different telescopes more easily. Download it. I'm going to upload it. And it still looks good. You get a little bit more scatter perhaps because there's an extra degree of freedom in the shape parameters. But if you're mixing and matching telescopes, sometimes this is preferable to having the apertures good for some and bad for others. Anyway, I want to give you those advanced skills, and they will be built into the updated labs. Okay, questions? Okay, lab 6. So let's see, I think I have it here. Yep, there's lab 6. And we start out, with the usual introductory stuff. Here's the playlist over here. Introductory videos, and then the tutorial videos, including one on how to use a spreadsheet. We start to introduce some spreadsheet skills in this lab because there's some repetitive calculations that would be painful without a spreadsheet. Go back to the lab. And then the next thing is you want to put in your lab 7 observation. So I'll walk you through that next. Lab 7 is a unique lab. It is, I think I have it up here. It's our most unique lab. They're going to measure the rotation curve and mass of the Milky Way. And I just think it's cool that we can actually do this at the survey level. This is a pretty advanced kind of thing, but it does require some knowledge of trig, but actually not too much. And they can get through the lab without actually understanding the details of the trigonometric functions. We'll talk more about it next time, but it's unique. We're doing spectroscopy, we're doing Doppler shift, we're doing radio, all sorts of unique things here. But we got to collect the data. I think it's here. No, not there. Procedure. Maybe it's here. Yeah. So there are tutorials on how to do it in here, but I'm just going to show you. So go to Skynet. Radio observing. So this is the first radio observation in the OPIS curriculum. Lab 9 will also use a radio observation to help measure Hubble's constant. The radio side's not as fleshed out as the optical side, and since we're deep into the construction of Skynet 2, we're not going to bring it up to par, but it's pretty easy to use. Adding a new observation, and what we're going to do is we're going to get spectra. Let me advance in time. Spectra at 12 locations along the galactic plane, from the galactic center out to almost 90 degrees. One observation every 8 degrees. And from these spectra, we're looking for cold hydrogen, neutral hydrogen emission. There's an emission line in the radio at around 21 centimeters, and the students will be measuring Doppler shifts from them. So let's start by going into galactic coordinates. And this is all in the videos and instructions. I'm just showing you quickly. And we'll start 0, 0, which is the galactic center. I want to name it something. I usually try to put the galactic longitude in the name, because we're going to do longitude 0, 8, 16, etc. And by putting in the name, it's easier to figure out which is which. The air mass chart doesn't work in galactic coordinates. My programmers refuse to fix it because it's fixed for Skynet 2, and they don't want to touch the Skynet 1 code. So don't freak out that there's no air mass chart. Save and continue. The next thing you do is you're picking your filter. On the optical side, you'd be picking your filter. On the radio side, it's a little different. We don't put a piece of glass in front of the radio telescope. We actually bring in a full spectrum, and you can manipulate it after the fact. For this, we're going to go into high resolution mode. To see that very narrow line and how it moves, you want to be in high resolution mode. And it actually gives you 2 spectra, each 15 megahertz side by side. It's the second one where we're going to see the line. Basically, just put in high resolution, leave everything the same. Save and continue. Pick a time account. And basically, you're just going to track the spot for about 2 seconds. The videos say 1 second, but I've overwritten in their notes saying do 2 seconds. Sometimes if you go too short, the system hiccups and you get nothing back. And it can still happen with 2 seconds. It's just less frequent. If students get an observation where nothing happened, they should just resubmit. Now, things to keep in mind, we only have one radio telescope at the moment. This is the 20-meter telescope at Green Bank Observatory. I think I'll pull up Lab 7 here. Yeah, this one right here. So 20 meters across, 6 stories tall, 150 tons, and they're going to move it around and observe the invisible universe, which is cool. And thanks to the DoD grant, we'll be integrating these all over the world, from about 12 meters to 30 meters in diameter. I've negotiated fractional access to each of them. So it's going to be pretty cool. First ever global network of radio telescopes for education. So basically just a 2-second spectrum. You submit, and let's take a look at one that's come back. Let's search my observations. Here's one at galactic longitude 16. We don't have our own data products yet, so we go to Green Bank's site. And basically here are the 2 spectra. It's this top one that we're interested in. I can go to the live spectrum mode. We can zero in on it. In the lab, students download it and upload it into one of our own measuring tools. Oh, there we go. So there's that hydrogen line, but we see kind of 2 or multiple blobs because we're intersecting different arms of the galaxy, each one with a different motion towards us. And next week, I'll show you how they make the measurements. There's a lot of background in Lab 7, but the execution is pretty straightforward. They end up with the rotation curve, and they can see it's not Keplerian, so the mass is distributed, and they can weigh the galaxy out to different radii, and we give them information going out to the LMC and SMC so they can touch on dark matter. So it's a cool lab in many respects. Okay, but that's how you put those observations in. Oh, I should say, that's how you put one in. Putting the next one in is really easy. Just bring it back up. You don't have to redo the whole thing. Just hit resubmit and change the galactic longitude to the next one, 8. Maybe change the name to GL8. and then just save, 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 save. Now 8's in there, and do it again for 16 and so forth, all the way out through 88. Each student will put 1 in. That makes sense? Okay. Now, lab 6. I've left us 19 minutes for lab 6, but I think I can do this here. Let's go back to the lab. Let's see. Again, the reminder to check their sources of errors in the previous labs. Yep. Okay, here we go. Goals of this lab. They're going to use so in the last lab, lab 5, they learned how to use R. Lyraes and Cepheids as standard candles and type 1As. In this lab, this is a practical application. They're going to use R. Lyraes and Cepheids that we give them to figure out the solar system's place in the galaxy and the galaxy's place in the universe, which is a continuation from lab 3. We learned that the Earth's not the center of the solar system. Now we're going to learn the solar system is not the center of, et cetera, et cetera. Our place in space, the theme. So we're going to give them R. Lyrae, variable stars, and globular clusters. And using what they learned, they're going to measure the distance to them. And through a tool that we've created, they'll create a top-down map of the Milky Way and see our place in it. And so they'll figure out, that we're not at the center. And in the second part, we're going to use those same R. Lyraes, globular clusters distribution to figure out the size of the Milky Way. And then in the next part of the lab, we're going to look at what were then called spiral nebulae, these little spirals we see in the sky. We now know they're galaxies just like our own, but back then we didn't know. Many people thought the Milky Way was the predominant object in the universe, and the spiral nebulae were just little things around us, kind of like the globs. And so here they're going to image them, and we talked about how to put the images in last time. Bring them up in Afterglow, measure their angular extent. We'll give them information on the Cepheid in there so they can calculate the distance and hence the physical size. And they compare it to the physical size of the Milky Way they just measured and see that we're not special. That's the theme. So this is the great debate of 1920, Curtis-Shapley debate. So in the first background section, we talk about the Harlow-Shapley and Heber-Curtis debate held at the Smithsonian in 1920. And here I summarize the arguments they made. Nothing was really resolved until years later. Let me just, instead of doing it verbally, where's my sheet of notes? Here it is. I'll just slide this over because I have a nice little table here. It kind of summarizes it quickly for you. So the 3 questions: is the sun at the center? What's the size of the Milky Way? Is the Milky Way unique? Shapley argued that the sun was not at the center. Correct about that. Heber said it was at the center, so he was wrong about that. And we'll use R. Lyraes to come up with the answer. Size of the Milky Way, Shapley said it was about 100 kiloparsecs across. Heber said it was 10. It's kind of influenced the previous answers. And the actual answer is kind of in the middle. It's 30, which is the middle in terms of factors. Curtis was about a factor of 3 too low. Shapley was about a factor of 3 too high, because in astronomy, 3 times 3 is 10. Just to keep in mind. And then in the last part of the debate, it really was kind of 2 debates where Shapley was making his case and Curtis was putting up a weak defense, and then Curtis was making his case. He was more interested in the spiral nebulae, and Shapley put up some weak defense. Is the Milky Way unique? Curtis said no. That the spiral nebulae are farther away than we think, and consequently they're physically bigger, comparable in size to the Milky Way. And since he was underestimating the size of the Milky Way, it was easier to come to that conclusion. But he got it right on that front. So 1 right, 1 tie, and the other right. Anyway, that's a quick summary of the history. First, 2 more background sections, 1 on the Milky Way, 1 on the spiral nebulae. So if we're going to use globular clusters, we have to explain what they are. And so you start with a cloud of gas that's maybe about 100,000 times the mass of the sun. And all these gas clouds are what I like to say stably unstable. You disturb them just a little bit and they collapse. And they're unstable on all scales then. As they collapse, they fragment, and the fragments fragment. And the fragment until you end up with about 100,000 little blobs, each of which will become a solar system, giving you something like this. Now, if this happened in the plane, and it does, in the plane of the Milky Way, gravitational shear forces tear them apart. Those are the open clusters, and they dissipate quickly. But these globs, I know you know this stuff again. I'm just kind of presenting it as you might to your students, but more quickly. These globs formed when the galaxy formed. So in this figure, this is on a much larger scale. The little yellow dots are globular clusters. So, this is a little yellow dot in this diagram. Here you have some primordial gigantic clouds of gas that merged and formed the early galaxy. As they were merging, little pockets collapsed, forming the globular clusters. Eventually, the gas settled down into a disk, but the globs were still floating around. And they float around on kind of random orbits, we call them. They're located up in the halo above the disk. But their extent should be about the same extent as the Milky Way. So if we can measure the distances to them and make a top-down projection, we'll end up with something like this. And the question is, where is the sun in this distribution? If it's at the center of the glob distribution, it's probably at the center of the galaxy. Or if it's in the outskirts, it's not. And the extent of this distribution is a proxy for the size of the Milky Way. And these are easier to observe because they're out of the plane. The plane is full of dust, so it's hard to do this kind of thing in the plane. Since they're out of the plane, we're good to go. So that's the first part of the lab. Second part's on the spiral nebulae, the most famous of which is Andromeda, but of course there are many, many of them out there. They've taken pictures of 5 of them, and those pictures should be ready, well, as many that are observable. And this figure should look familiar. We've been drilling this geometry over and over again. We're going to give them information on the Cepheid in each of these spirals. They're going to calculate the distance. And then we want to know the physical size, the diameter of the galaxy. So again, it's a ratio. The diameter of the galaxy divided by the circumference of this big circle is equal to the angular size, which they measure in afterglow, divided by 360. Just this right here. Circumference is 2 pi times the distance. And so here, diameter is 2 pi times the distance, which they're going to calculate from a Cepheid, times theta, which they have to convert to degrees, divided by 360. Okay, those are the background sections. So procedure, 11 minutes. I'm going to make it. So in the procedure, we've given them 30 globular clusters. Actually, I'm going to copy this into a spreadsheet so you see how they do it. Let me get out of answer key mode because I don't want to copy all that. Oh, Cengage. Gotta load it back up to get out of answer key mode. So we've picked 30 globs. We give them the longitude, latitude, and the apparent magnitude of an R Lyra in that glob. And we set them up a little bit, what is longitude, latitude? I kind of hate this because it's giving away the answer a little bit in defining the coordinate system. This coordinate system only works because we're not at the center of the galaxy. And that's one of the things they're trying to figure out. But anyway, longitude 0 is pointing at the center. And so the angle, greater longitude, you're moving away from the center, greater latitude, you're moving out of the plane. Here it is from our point of view. This is the full sky projected onto a flat surface. There's 0, 0. Longitude runs from minus 180 to 180, latitude minus 90 to plus 90. So just teaching them the coordinate system. We have a tutorial here on how to do this in an Excel spreadsheet that I'll just show you. I'm going to copy the stuff. Going to go here and I'm going to paste, though I think you have to paste special as text, else those boxes, the entry boxes will come in here as well. You don't want that. And actually, let me back out and do it one more time. Let's get the headers as well. Paste special as text. And for this top round, I'm gonna, I'm trying to remember, it's there's a wraparound. Format cells.
I think it was in the original, if you go back to the file or home, yeah, wrap text was there.
There it is, just to make it easier to see. Okay, and so galactic longitude, galactic latitude, average mag. So they need to know the absolute mag, and for our Lyraes, they're all 0.75. And so we show them how to, enter numbers, enter equations, drag it. Then you calculate the distance, and the equation from the previous lab is 0.01 times 1.585 raised to the power of little m minus big M. I'm doing it quick for you, but the video walks them through it slowly. So now we have all the distances. They don't have to do them all by hand, and it's good for them to learn some basic spreadsheet skills. And I'm going to put this off to the side for a second. And so then we have a tool. It is called scatter. And I'm copying the longitudes and latitudes now. Put them in there. Copying the distances next. Put them in here. And what this does is it takes the two angles and the distance and turns it into a top-down projection. So you're now above the plane of the Milky Way looking down. You see the distribution here. And it's a very simple thing to model. You kind of eyeball the center. You eyeball the size. And I think the canonical, I did it really crudely. The canonical value is 8.1. And the galaxy somewhere around 36 is reasonable. And so, they eyeball it there. And then going back to the lab, we ask them questions, sample calculation for the distance. They upload the PNG of what we just made. Estimate the distance between us and the center. We came up with something around 8. Google the true value, 8.1. Calculate percent error, sources of error. The source of error is difficulty finding a centroid with only 30 points. So the human eye is actually pretty good. You give the human eye 30 points, it can centroid it pretty well. But that's the dominant source of error. Who is more correct about the solar system's place in the Milky Way? That would be Shapley. And then the second part, estimate the distance across the distribution using our little simple modeling tool. We came up with 36. Google the true value, I think is 34. Calculate percent error. Most significant source of error is where is the edge of the distribution. There are a few points around the edge, so you have to kind of ballpark it. Who is more correct? And in the update, I'm providing some extra text, so it's clear. In terms of a difference, Curtis was correct, but in terms of a factor, they're both off by a factor of 3. The updated text, it tells them think in terms of the factors. So it's neither in this case. 5 minutes, I'm going to make it. Here are the 5 spiral nebulae they observed. They're all L-star galaxies on purpose for reasons you'll see. Here's the table. Did you successfully observe it? And again, now we're giving them a Cepheid. Here's the average magnitude and the period. Remember from the last lab, from the period, you can calculate the absolute magnitude. And then again, from the apparent and the absolute, you can get the distance just like we did above. There are only 5 of these. They can do them by hand, or they can put them into a spreadsheet. And in the spreadsheet tutorial, we show them how. And then what they need to do is they measure the angular diameter in arc minutes, convert it to degrees, and using this geometry ratio approach that they've done many times now, they calculate the physical size of the galaxy. Measuring the angular size of the galaxy is something they know how to do. Let me bring one up. I think one of the ones they observe is M66. And what we tell them to do in the lab is it's sometimes hard to see the edges. So we tell them to change the saturation level to 90, making that easier. And then they can just use the measuring tool, which they've already learned how to do, from one edge of the galaxy to the other. So this one's about 7 arc minutes. Now, if it's off the edge of the screen, they can measure from the center to the edge and double it. And that's described in the lab as well. So just to wrap it up, sample calculation. Here we have sample calculation for the absolute magnitude from the period, the distance. This is sign your name, but then those 2 calculations. Down here they show calculation for the diameter. Most significant source of error is estimating the edges of the galaxy. It's kind of fuzzy and faint out there. How does this compare to the Milky Way? How did the size as you calculated compare to the size of the Milky Way? Is the Milky Way many times larger, many times smaller, or typical? And it's typical. The sizes they should get will range from about 20 to 40 or 50, and Milky Way's low 30s. And so they'll say it's typical. Who is more correct about the Milky Way's place in the universe? Curtis, that we're not special. Yeah, I did with 2 minutes to spare, even though I spent 30 minutes having fun talking about other things. Any questions? It's pretty straightforward. I think it's a good fundamental application of the skills they just learned. So you don't want to do lab 6 without lab 5. If you're picking and choosing, often you do those 2 together. Lab 5 also leads into the type 1A stuff that we do later on in the sequence with cosmology. All right, well, if there are no questions, I'm going to stick around for my TAs, but I'll see you next week, and we'll do some radio astronomy next week. Our most unique lab, so prepare yourself for extreme uniqueness.
Yay.
Thank you very much. Appreciate it.
Thanks. Thanks.
My
Thanks,
pleasure.
Dan.
Was muted. We're, I mean, at Appalachia, we're very introductory astronomy, right? In the first semester.
Mhm.
So they're just looking at the moon right now and things like that. So like doing HR diagrams and stuff is way over their head at
Right.
this point.
Yes.
But we're getting them engaged to that point. And actually on Sunday, I'm actually doing a little talk on I did a little talk on like Galilean revolution and how being an astronomer back in the 1500s was actually kind of dangerous, right?
Mhm.
So I talked about Giordano Bruno and those those folks. But we are starting to get into light and what light means, because we only have 4 labs left in this semester.
Yeah.
Where they go on to like stars and galaxies in the spring. And Do you have any advice as far as like that? Because I wanted to show them a little bit of a brief. I talked to Elise about this. Wanted to show them kind of like how diffraction gratings work, but a basic watered down
Sure.
kind of, yeah.
So, spectroscopy experience. Uh, when I teach and lecture, I bring in element lamps and hand out diffraction gratings and have them identify the elements. But I have spectra up on the screen and say, "What's this one?" And they get they look through the diffraction grating and they say, "Oh, okay, that's neon. Okay, that's
Yeah.
helium." And so if they can identify it from the back of the room, we can do it from halfway across the universe. That's a very simple introductory thing. In terms of a lab experience, a lot of introductory lab sequences, they do a spectroscopy lab and it's using element lamps and maybe making some measurements on top of the very qualitative thing I just described. But in OPIS, we decided we're going to do the spectroscopy as part of the lab 7, radio lab 7, rotation curve of the Milky Way. So we take a different approach to spectroscopy, in part because optical spectrographs, we don't know how to we don't have any of those on Skynet yet. They're very challenging. But in the radio, you can't help it. You get a spectrum at every observation, whether you want one or not. and this leads into all sorts of stuff. The Lab 9 that I'm still producing, now they'll image galaxies, they'll take a spectrum. It will be a special kind of spectrum on-off to cancel out instrumental oscillations so they can see the faint hydrogen line for more distant galaxies and measure redshifts and get Hubble's law. And we do lots of stuff with spectroscopy in the radio in the MWU course as well.
Right on.
Yeah, so you'll get some spectroscopy, just a very different type of spectroscopy next week. And the MWU course, it's not necessarily going to fit in your giant survey. I know you split it across 2 semesters, so you may be able to fit some elements in if you wanted to. If you're doing like OPIS in 1 semester, there's no time for MWU. But since you split it, in the MWU curriculum, we have solar system stuff, star stuff, and galaxy stuff. So there are other things you can build in. Like we measure the temperature of the moon in radio. We learn how to image the moon and planets in color and learn things about surface compositions, etc.
I think the the program here is kind of dynamic right now, where we have a large number. Do you know Don Smith? In fact, I emailed.
Mm-hmm.
Yeah, I actually emailed him this morning, and I said we have probably our enrollment in physics and astronomy is close to 2,000 students. And I know 200, there's 250 just in intro astronomy. So, this is like AST 101, like, planets.
Yep.
The sun and planets, nothing beyond that. And so, but I think it's really dynamic. And I think, of course, Elise Weaver, who is the director, is trying to figure out like how to manage that side of astronomy. And it could be very possible that Dan Cadent might be retiring soon, which is reasonable. But yeah, so OPIS could be done in 1 semester, I think, potentially.
Well, yeah. Well, you have, since you teach introductory astronomy kind of the way I like it, where it's split across 2 semesters. And so splitting, you have a number of options available to you. If you want the labs to match up with the lectures, you'd take the OPIS curriculum and you'd split it between the 2 semesters, and you may grab some MWU stuff and mix it in, or you save MWU for a follow-up course, whether it's some pre-existing course that you have for students who have come back. The idea with MWU is it is meant for a smaller population of students, so we can give them a lot more telescope time per student. If it's 250 students every semester doing a full MWU, it's like 4 times the telescope time per student. We have to figure out finances there.
Yeah, it's not going to work.
But presumably, out of your 250 students per semester, a bunch come back and become majors, or they come back for just another course out of interest. I don't know if you have such a course like that on the books, or maybe create one. That's what I did at Chapel Hill. I created a course called Astrophotography of the Multi-Wavelength Universe, and it's just the MWU activities. And we teach it very different than OPIS. It's group work. So in a group, you may have someone who's skilled with images, color combination and artistic stuff. You may have someone who's mathy, someone who's physicsy, someone who's a good writer because their work products are blogs. And we actually teach it, everyone gets an A as long as they turn their stuff on time and do revisions on time, which takes the stress out. And this is a separate conversation, but what we're finding on the education research side is if you want to turn someone into a STEM major, there are 2 factors. And it's not the content knowledge. They'll learn that along the way. It's self-efficacy. Yes, I can do this. And OPIS kicks butt in that. And so does MWU. But the second ingredient you need is after you convince them they can do it, you got to convince them they like doing it. And that's STEM attitudes. OPIS doesn't move attitudes, it turns out. It's hard in the literature. It's hard to move attitudes. They move super slowly, except when they don't. It's a punctuated equilibrium kind of thing, like Stephen Jay Gould's theory of evolution. The evolution creeps along until you have an event, and then boom, something big happens. And our RIRA summer program, we do these attitude surveys, and something big is happening. Like in a 1-week span, you shouldn't be able to move attitudes at all. And we have statistically significant big jumps in attitudes about STEM and the self-efficacy. And they all come back and become majors. The formula holds. MWU, the goal there is to somehow bottle that magic and put it in the classroom. And our preliminary results suggest that we might be moving attitudes. But it's a very different kind of thing. It's group work. It's about star formation and evolution, galaxy evolution. It's all the fuzzy, nebular stuff instead of the cosmic distance ladder.
Yeah, it's really combining all the pieces and and being able, I mean, I think it gives a sense of like ownership to like the student to be able to go out like and who knows, like talk to their friend in construction management or something, and be like, yeah, I know how that star is made because I understand the physics behind it. And it's really cool. We had obviously I can't name names, but we had a few students in my sections here that were kind of struggling a little bit. They weren't showing up. They were just kind of lazy. I mean, I do Sunday night, astronomy classes. So, I mean, I honestly can't really blame them. Oh, yeah. I wouldn't want to show up either, but I have to. That's what I'm paid for.
Right. Yeah, we learned at Chapel Hill. When we moved our labs to the day time slot instead of nighttime, enrollments blossomed.
Yeah. And they all hated it. Well, most of them, but now they love it because like the OPIS like track is really like between that and then a little bit of like classroom engagement and telescope time, like when they get to go out and use the telescopes, which is rare in Boone because of our weather.
Yep.
Kind of sucks. But yeah, I mean, it really like I have seen students that didn't show up like a lot at the beginning of the semester. They they didn't drop the class.
Hmm.
Like they're now showing up all the time and they're staying like even until the very end of our lab period.
You said a couple things there. These experiences plus a little bit of telescope, actual in front of you telescope time, a little bit of lecture. And that's what we're really advocating for. We're doing a meeting, a big meeting in May at Chapel Hill. I hope you come. And where we're really kind of pushing this philosophy that we're doing introductory astronomy all wrong. And the lecture should become secondary, the textbook tertiary to these explorations where they learn what science really is by doing. And it gets people excited. The second thing you hinted at is sometimes when you do have maybe a higher number of drops initially, people who signed up thinking, I'm going to just look at pretty pictures and learn constellations. And they're like, oh, crap, he's making me do science. You do lose a few people. But word of mouth, for those who stay behind and they have this amazing experience, word of mouth grows. And particularly if you work closely with your academic advising people, you can get huge boosts in enrollment. Like take Daryl Jansen at Saskatoon, who's one of the big players in our MWU effort. He went from 400 students a year to now 1250. And it's all OPIS driven gains. Now, many places they have no boosted enrollment because they don't permit it. They cap the classes, et cetera. But if your goal is to boost enrollments, if you do it right, OPIS can be a vehicle for doing that. And then when you have 3 times as many students, you go back and say, we need more faculty, et cetera.
Yeah, hi Dan. Sorry, I've been listening into your conversation.
Good.
Is there flexibility in the OPIS curriculum, such as like if I want to add something from maybe MWU?
Yes.
There's okay.
Yep. And so some people, the education research team hates this because they're trying to study it, and it's so hard to study when people are mixing and matching, but that's their problem. So keep in mind, MWU is still being built. It's still very rough, but in a year or two, it's going to be pretty solid. And you can take these units and do them with your students. They're not in WebAssign. They're because the MWU is kind of designed for blog production as the work product instead of like auto grading. But you can take these things and build them in. Some don't take a lot of telescope time. Some do take a tremendous amount of telescope time. And so that's the only caveat. Depending on what you choose to do, the students may run out of time. So we have to think creatively. Like the astrophotography elements can eat up a lot of time. But at the same time, a lot of it can be done archivally with images other people have collected. And that may sound boring, but what we've learned, quite to our surprise, in OPIS, you're talking about ownership. And in OPIS, it comes from collecting the images themselves from professional equipment right alongside the pros. But what we learned in MWU, by the end of the semester, they didn't care who in the group took the data. They pool their time so they can do some pretty extraordinary things. And they didn't care about that. But they still feel ownership, even if they're grabbing archival data. We also mix in some archival infrared images because you get a lot of science boost when you combine the infrared with the optical. It was the process of putting it all together. Everyone does it differently. They color things differently. They tweak the brightness and contrast and color schemes, and they make their own piece of scientific art. And that's where the ownership feeling is coming from in MWU. Anyway.
No, I mean, that's amazing. That really is.
Yeah, I have a whole team that's writing paper after paper after paper, going in the lead. Not just there are like 1,000 education journals out there. Most are crap, but they're going in the lead education journals. We're doing something, and we're really hoping to funnel it into a revolution in what's done at the survey level. Instead of 3 credits lecture with some lab stuff, come at night and we'll do something. Flip the model completely around, because students are going to forget everything or almost everything you teach them in astronomy because there's no relevance in their everyday life. And the Harvard video just is evidence of that. So let's move away from content. I'm actually being bold and saying content in intro astro doesn't matter at all. It doesn't matter what astronomy you choose to teach them. The thing that they could gain if you're bold enough to try it and flexible enough to deal with uncurated data sets, that's the challenge, is they're going to learn how to do, they're going to learn what science is, and you only learn what science is by doing it, not by listening to what other scientists produced.
I agree wholeheartedly. Have you met Dom Widget?
I know Don, I know of him. I don't think I've met him, actually.
Okay. Yeah, he came to North Carolina to give a talk. He was the one, he did the Sandia National Lab.
He's Chris Clemens' advisor. Chris Clemens is our provost, astronomer.
Oh, okay.
Yeah. When Chris was a grad student, he worked with Don.
Yeah. But I don't know if he still does this, but he assigns his inter-astro students like to come up with like a piece of art or poetry or something that like, you know, like for them conveys what all of this means, right?
Mm-hmm.
And so it's really, I think, powerful way of educating. And I don't know if it'll work in traditional astronomy classes, but as you said, I mean, like changing the game and yeah, I mean, we need to think about this. I mean,
But,
teach from, yeah, go ahead.
yeah, two things I can say. One is when they rebuilt the UNC curriculum to, in a sneaky way, muscle out science requirements, because there was the historians and English majors who rebuilt our graduation rules. One of the new focus capacities, it's no longer you have to take a science class and this class. It's you have to meet these capacities. One is creative production. And they're thinking, oh, this is going to be great because no science classes are going to sneak in here. Well, damn, MWU said. And the second thing I can say, and this may sound sexist, and so in stereotypical, and just forgive me for that, but this is what the research is showing. In general, guys are more drawn. I'm not saying better. I'm just saying more drawn to the mathy side of all this. And women are more drawn to the imaging side of all this. And so by offering something like MWU, you're reaching out to audiences that you may not have been getting before due to different interests. And you can put the whole guys, girls thing aside. It's just everyone comes with different skill sets and different interests. As I was saying, some people may be good writers and explainers of science. Some people may be good at the image creation, the artistry. Some people may be good at the physical inference, and others at the mathematical calculations. And a curriculum like MWU and other things like it that you could imagine caters to everybody, particularly if they're working in groups. Everyone brings something to the table and they work as a team using their strengths.
Yeah, absolutely. Absolutely. I don't want to delay your TAs.
Shannon's here. So I guess I'll let you go and we'll switch over to finding the rest of our TAs.
Yeah. I was having to look for mine the other day, and then I ended up having to teach by myself. So, you know, that was fun.
But I like how you think about these things, and so once you get Opus under your belt, I really hope you join the MW group, and I hope you come to the May meeting, because it's not just going to be learning how to do these things. We're going to be talking about these topics, and we're actually going to produce a decadal plan. If I can get 200 people there, they're going to be working on table. We're going to learn all sorts of we're going to do workshops and do things, OPIS things, MWU things. But at the same time, we're going to have discussions about all these kind of subtle topics. And we're all going to, each table is going to produce a 2-page document. I'm going to take the third day and going to write a document that we're going to put together into a decadal plan for how Intro Astro needs to be burned to the ground and rebuilt. And so I'd love your participation.
I'm coming.
Good. It's May 2021, 22.
All
And
right.
we'll be announcing it soon.
Yeah. All right.
All right. I'm going to stop the
Was it-
recording.